Okay, well, we our proposal for the seminar today was that we would give at least sort of three independent short presentations with the intention of seeing sort of where these ideas overlap and where they might be imply approaches or applications of the ideas in somewhat different areas. So the last presentation by Jesus was on interaction theory, and I think I made a number of comments during that meeting that I thought that it was very important sort of to approach relativistic dynamics with this idea of interaction. So that's sort of where my head is. On the other hand, also the algebra that's involved in the approach that Boschevich was taking has considerable overlap with the ideas from geometric algebra that Dr. Sobczyk has been presenting. So I'm sort of optimistic there as well to see to what extent the mathematical formalisms are similar. And in terms of mathematical formalisms, one of the last comments I think that Jesus made during the presentation last time was the relevance of monad theory, monads in category theory. And I've done a little bit of background reading on that, and I am quite intrigued to understand how monads, how the concept of monad might be related to the concept of process as presented by Boschevich in other contexts. So I think there is some potential for overlap for sure. And I'm not sure how we should proceed. Maybe Dr. Sobczyk, you'd like to start with your comments on nilpotents?
Yeah, actually, I'm not presenting anything too much that I presented before, but I would like to emphasize the importance of the nilpotents and idempotents. In particular, I'm going to start with the same. I can maybe share my screen here.
Yes.
And we can get started here. Oh, wait a minute, maybe this is, no, this is the wrong one. That's just a second here.
So far, we still have your video.
Yeah, right. See, is this what I want? Oh, wait a minute, see. Yeah, I thought I had it on my, I'm trying to find the, yeah, let me wait just a second, and I try to find the, I don't know why it's not on my desktop here.
Is it the file that you're looking for?
Yeah, the file that I sent out yesterday.
Ah, yes.
I should have it right. Yeah, here it is. Okay, so all I have to do, I guess, is share my screen. You can be able to see it then. Okay, let's see here. Okay, that's what I want.
That looks good.
Okay, so like I say, I've titled it Nilpotent Geometric Algebras. And I'm just offering a nilpotent, of course, is any algebraic quantity x such that its squared is equal to 0. And two nilpotents are said to be anti-commutative if, when you multiply them together, a1, a2 plus a2, a1 is equal to 0. So now I'd like to construct other elements which aren't nilpotents from nilpotents. Everything then, in fact, what my goal is to represent any matrix as a product of nilpotents. Everything of a mate defined by a matrix can be represented in terms of products of nilpotents. In particular, I like to demonstrate that in the most simplest cases of the polyalgebra, well, the neutral geometric algebras, and also the Dirac algebra. So that's all I wish to talk about today, and I've talked a lot about it before. So, okay, so the next definition here then, the set of mutually anti-commuting nilpotents, A1 up to AN, is said to be linearly independent over the real numbers or the complex numbers if when you multiply them together, it's not equal to 0. So that's a way of characterizing linearly independence of vectors. So in this case, linearly independence of null vectors or nilpotents. Okay, so they generate a Grassmann algebra then. So we're taking a set of n nilpotents which are anti-commutative and defines the Grassmann algebra. If you take all products of starting with the one vectors and you generate two vectors by multiplying any pair of them and so on, but they're all satisfy this first property here. Now, this is a very important definition. A pair of nilpotents, A and B, are said to be algebraically compatible or dual. That's the more general terminology people use that Dr. Ozevich was always using as well. And I characterize duality by this condition, AB plus BA is equal to 1. So first of all, anti-commutivity is characterized by A1 times A2, A2 plus A1 is equal to 0. So again, this is a set of anti-commuting vectors, n of them. And now we're talking about, well, now I'm looking just a pair here. So a pair of nilpotents are said to be algebraically compatible if instead of getting 0, you get AB plus BA is equal to 1. Okay, well, these two rules, this first rule here and the second rule here, are what I need to define a multiplication table. So here we have a pair of algebraically compatible nilpotents. Okay, so in the table, you can see it's A squared is equal to 0. AB is just AB because it's part of this process here. If you look at A times AB, well, you see we are assuming that the nilpotents obey all the usual rules of matrix multiplication. So A times AB, it's associative, so you can write that as A squared times B, but A squared is equal to 0. So you get A times AB is equal to 0. And now if we take A and multiply it by both sides of this expression on the left, then of course what you get is A squared B, which we know is equal to 0, plus ABA is equal to A. So that's why we have the rule A times B, A times BA is equal to A, because we're multiplying A times this expression number 1 here. So that's how we get the rule A times BA is equal to 1, because that's part of A times AB is equal to 0. So the first term drops out, and that we must have then A times BA is equal to A then. And then we just do the same thing for B. We have B times A is BA. now if we multiply this table here by its property by B, then we get BAB, but we have B squared A, that's 0. So we have then that B times BA was equal to 0 by associative log n. B times BA is equal to 0. And now if I multiply everything, let's see what happens when I multiply by BA. Well, here, AB, well, you can see AB, if we multiply this expression by AB, we get AB squared. But then we have AB times BA. Again, we can eliminate the second term because AB times BA, we get a B squared, and that's 0. So we have AB times AB is just equal to AB by, again, multiplying this expression by AB. Okay. And we also have AB times BA is equal to 0. Well, because A times B squared is 0. So we have a 0 in the expression. We get 0 then. And finally, the multiplication of BA times A, well, that's BA squared, that's 0. BAB, well, we've already discovered BAB is equal to B, right? BAB is equal to B because when we multiply this expression by B, we get, on this side, we get BA squared, and here we have BA then. Well, here we have, okay, is that clear? I think it's clear,
Sure.
right? Okay, so we can go to the next slide then. Okay, so now what I'm doing is developing the 2x2 matrices. Well, I'm actually developing the neutral. It has been called the mother geometric algebra of two-dimensional space, G11, okay? So what I'm doing here is developing the idea of a spectral basis. So if I take 1A, multiply that on the right or on the left times BA times 1 times B. Now, I mean, that's a column vector with 1 and a nilpotent in it. So I'm using all the usual rules of matrix algebra together with the new rules of these nilpotents, which I've gone over in the last slide. So let's see what we get here. We get, well, if I multiply, again, it's associative, so I am free to multiply by this column vector 1A, and what I get is I get BA and A. Okay, so I get BA here, and I get ABA. Well, remember, ABA is just equal to A. But remember that that's also an idempotent. So I can also write this as BA times BA. We saw the table BA squared is equal to BA. So I can also put BA into the right side, and I get BA, and I get BAB. Well, BAB was equal to B. And then the bottom, then I get ABA. Well, that's equal to A. And then I get AB here. So you see, then I've gone from the column vector 1A with BA in the middle, which is an idempotent, times 1A times B, and I get this expression BA, B, A, and AB. Okay, so that is what I call the spectral basis of the geometric algebra 1, G1, 1, neutral geometric algebra. Okay, well, what do I call that? Well, let's let G be a 2x2 matrix over the real numbers, okay? So as a matrix then, a matrix in the matrix algebra of M2R is just G11, G12, G21, G22, the usual 2x2 matrix over the real numbers. Okay, now what I do, now I put G, that's the geometric number, which is going to represent that 2x2 matrix. And how do I get that? Well, I write G, that's the geometric number I'm looking for in this geometric algebra G11. I multiply it by G, and on the right by BA. Well, you can see that's exactly what I'm just changing this into a row vector, BAA, and I'm changing the other side into instead of writing BAB as a row vector, I'm writing it as a column vector. Well, when I do that, note what I get. I multiply it out using the rules in the table, and I get G11BA. Well, that corresponds to BA, you see. So it's G11BA plus G12B, that's this term here. And I get G21A, well, that's this G21 times A here. And I get G22AB. So you can see, I call that the spectral basis of the coordinate matrices, the 2x2 coordinate matrices in M2R. That's pretty clear, I suppose. If there are any questions, then I'm going over this very slowly because it's easy to not see this, but it's pretty easy to understand. So I say this is the coordinate matrix of this geometric number, which I've defined then in that way.
When you say coordinate matrix,
Of this geometric number.
There's more than one coordinate matrix.
Oh, sure. You know, we can.
So G11 has what? How many basis elements generate?
Well, this matrix basis consists of 4 elements: B, A, B, A, and AB. These are all in this geometric algebra G11. So for example, A is represented by 0, 0, 1, 0, you see. So that's the matrix. If you just put G11 equal to 0, put G12 is equal to 0, put G21 equal to 1, and put G22 is equal to 0, then you get the element A.
Mhm.
Okay.
Yeah.
And
So you didn't actually number that expression, but the third, the equations there below the third formula.
yeah, the third formula is just putting together 1 and 2 here from the last. Okay, well, it's a consequence of this multiplication table here. Okay, so I'm just, again, I'm taking a 2x2 matrix with BA, the idempotent, A, G, B, A, B, and then I multiply it out using this multiplicate, and we get exactly this expression. That's why I call this matrix 2x2 real matrix, the coordinate matrix of this geometric number with respect to this basis, spectral basis, to which I call BABAAB, which I generated in that way then.
Excuse me, one question. I don't understand. What are A and B? Are vectors?
A and B are nilpotents. A squared is equal to 0, B squared is equal to 0, which are compatible. So A and B satisfy this property here.
But what kind of objects are they?
Well, I consider them to be in the Grossman algebra G2. Okay, so we have A is in a Grossman algebra, and G and B is in the compatible Grossman algebra with one vector in it. Okay, they're compatible Grossman algebras because so that's right. So A is just a single element in the Grossman algebra G1. Well, I'm using almost the same notation, I guess. Could be confusing here. Yeah, you see there's a difference. So this is the Grossman algebra generated by just one nilpotent, A. And the dual or the compatible Grossman algebra is generated, that's also G1, generated by a single element, B. And they're compatible elements because they satisfy, well, now we're putting the two Grossman algebras together. So we have AB plus BA is equal to 1 then. Okay, but
Dr. Cruz, I think they can be interpreted indeed as being vector. Of course, has to be formulated appropriately. but I think it could.
Yeah, well, I'm trying to be, I've gone over this before, but it, you know, it's easy to not see it right away, but it's pretty. So what I'm doing is I'm constructing what I call the coordinate matrices of an element geometric number in the neutral geometric algebra. Now, okay, if we just, okay, here you go. So here, so with respect to the spectral basis, the null vector A is just 0, 0, 1, 0. Well, you can see how that works. That's this element here. Well, like the general element is given by this. Okay, so A then is this matrix. B is represented, the matrix of B is 0, 1, 1, 0, 0. Okay, that's B here. Okay, BA is just, that's the idempotent. BA squared, remember from the table, BA times BA is equal to BA. It's an idempotent. So you see a matrix, a 2 by 2 matrix consists of the product of BA, BA, and AB. They're geometric numbers now. So again, the matrix of the nilpotent A is just 0, 0, 1, 0, and so on and so on. And so you see that, right? That's just follows from 2 here in this line here. Is that clear?
But in your expression number 1 on the previous page, yes, I mean, some question might arise as to what is the multiplication AB?
Okay.
Like,
Well,
especially
I'm
since
really
you said that
defining,
they are,
like
you
I
said
say,
that they are, but you said A is in G1 and B is in is a compatible G1, but then what is the multiplication
okay.
in your
Well, the
expression 1?
multiplication of the A's and the B's are all the same as multiplication of matrices. Right away, I assume that all the rules of matrix multiplication, that's right, I'm defining this multiplication by the rules of matrix multiplication. I don't want to go into the definition of matrix multiplication or field or anything.
Yeah, but even without mentioning matrices, I mean, you're presuming some ring, right?
That's right. Yeah, that's right.
Uh,
So A and
and
B.
the ring, A and B are elements of a ring.
That's right. Well, actually, A and B
You
are
haven't
elements of
really
this-
said much other than that they're compatible. You haven't said much about them.
But the enveloping algebra is associative, so the product has got to be associative.
Yes.
Otherwise, everything has to be interpreted differently.
Yeah, well, that's right. I'm not trying to be rigorous because we all know matrix multiplication, the rules of matrix multiplication. So I'm trying to, omit. Okay, yeah. Well, you can see it. This is the geometric algebra G11 that we're really defining. Okay, and so A and B are just nilpotents in this geometric algebra G11. Okay, so
Well, but wouldn't you say that A and B are elements of a ring,
okay,
and that-
that's fine.
and
But
that
G11
A
is
and
a
B,
ring.
and you've also said that A and B are both nilpotent,
Yeah,
and you've also said that A and B are compatible.
and that's by this definition. Well, you
And
see,
so-
I have to make
so-
definitions, some definitions here. That's
Yeah.
this.
So
So we're
the
multiplying two Grossman algebras together, compatible Grossman algebras then.
but did you use the fact that they are anti-commutative?
No, no, I haven't, but let me go a little further. You'll see where that comes up. Okay. Okay, now look what I'm doing here. I define an element, a new element I call E equal to A plus B. Okay. And I define an element F equal to A minus B. Well, of course, the matrices of that then is just 1, 1. Okay, so you can see if you have the matrix with 1, 1 here, A plus B is 1, 1. Okay, well, of course, that's a matrix. When you square that matrix, you get the identity. Okay, and if you take A minus B, well, then you get a matrix 1 minus 1 here. And of course, that's just the Pauli matrix of E1 then. Okay, do you see? So, well, of course, if you multiply these matrices together, 1, 1, and 1 minus 1, they're anti-commutative, okay? So I'm defining the element as a geometric algebra G11 as A plus B and F as A minus B. So you can see this geometric algebra has a basis, the spectral basis, which has an idempotent BA, AB, A, and B, but the basic construct materials which we're constructing that 2x2 matrices are nilpotents and idempotents. Okay, yeah, okay, it's a ring and you know, anything you want to call it, but it's the geometric, that's what defines the geometric algebra G11. Okay, so again, the standard basis of the geometric algebra G11, which we've constructed by two nilpotents, A and B, which are compatible because they satisfy that property. That, okay, you can see, what is that property? BA plus AB, that's the identity matrix. So I'm identifying the identity matrix in 2x2 with 1. Okay, that's, okay, so it's clear now what I'm doing, right?
Mhm.
But that's
think
true.
so.
I'm using a little bit of non-conventional terminology because you can just, you know, start going in circles about rings, fields, integral domains, and the rest of it. But it's really not necessary. What's necessary, okay, the idea of a Grossman algebra of one element has one idempotent, A squared equal to 0. And you have a dual Grossman algebra consisting of B, which has it's a nilpotent, B squared is equal to 0. We say those Grossman algebras are compatible because they satisfy AB plus BA is equal to 1. Okay, well, then you see I'm putting together these two Grossman algebras to get the neutral Grossman algebras G11. Again, the spectral basis is this BABAAB. Okay, that's idempotent. That's an idempotent because BA times BA is equal to 1. BA times BA is equal to 1. AB times AB is equal to 1. Yeah, AB times AB is equal to 1. So you see, I'm just characterizing the properties of these basic elements. The nilpotent matrix, compatible nilpotents. The idempotent, well, okay, BA is just 1, 0, 0, 0. AB is 0, 0, 0, 1. Okay, so it's nothing really deep or anything, but it is, no one does that. So that's why people find it strange, I guess. Okay, well, you get E squared is equal to 1. Well, that's just the 1, 1. Well, that's just the matrix, the Pauli matrix E1. I'm not making such a great distinction between a Pauli matrix and a geometric number. I'm identifying with the unit vector E1, okay? Okay, so that's why I say the standard basis of the geometric algebra G11 is EF, a vector which has square 1 and a vector which has square minus 1, okay? But again, that just follows from this definition here. So I'm saying a matrix really at the most fundamental level is constructed from nilpotents, two nilpotents in the case of 2x2 matrices, which are compatible because again, they satisfy this basic compatibility property of nilpotents, which I call number 1 property. Okay, well, we can go on. Okay, so I define, well, you can see now, so the standard basis of G11 consists of two anti-commuting vectors which satisfy these properties. And that's the usual way a Clifford algebra with signature 111 is defined in terms of a quadratic form. Well, I'm not even talking about quadratic forms, but that's the usual way people talk about it, of course. So Okay, I define this new element, which is U. Well, that's a bivector. E times F is a bivector because A and B or E and F are anti-commutative. Okay, EF is equal to minus FE. Well, you can check that. That all follows from the rules of, if you look at the, well, that's the polyalgebra. We're getting close to the polyalgebra now. Okay, so now we can identify, okay, let's look at U plus. Okay, so U then is a bivector in G11. Well, that's the standard basis of G11, 1, E, F, and then the bivector, E times F. Okay, you can see how that works then. Okay, so I call U plus B times A, 1/2, 1 plus. Note what I'm doing here. Remember, E was defined as A plus B. F was defined as A minus B. Well, if you multiply it out, you get 1/2, 1 plus EF. Well, EF, if you square EF, you get 1. Okay, a vector times an anti-commutative vector F, which has square minus 1. Well, that has square 1. So here we have U of a bivector which has square plus 1. Okay, a Euclidean bivector has square minus 1, but this bivector in G11 has square plus 1. Okay, now I'm just repeating this. Oh, now I'm going to express the spectral bases that I wrote in terms of nilpotents here. I'm going to express that in terms of the standard basis then. Okay, so in the standard basis, E1 is just 0, 1, 1, 0. Okay, well, you can see that's usually what we call the Pauli matrix sigma 1. Okay, E2. Okay, well, now you see what we're doing here. Actually, you have to complexify. I multiply I introduce the imaginary number as square root of -1, and I multiply it times F, and I get the usual matrix representation of, well, the Pauli matrix sigma 2. Okay, so in terms of E and F, E2 is just I times F, I minus 1, I minus I. E3 is 1 minus 1. Okay, well, that's the standard these are the standard Pauli matrices which we've spent a lot of time on already, so I don't, but you can see how they arise then from two anti-commuting compatible nilpotents A and B, or in this case A1 and B1. I can subscript an A1 and B1 now. Okay.
So when you introduced the imaginary unit, you didn't attempt to make it an element of the algebra. Right?
Not yet, not yet. But that's what I'll do the next
You
slide.
spoke about it as a scalar.
Yeah, that's right. Well, it's just the complex. It's just I equal to square root of -1. So it commutes with everything in the algebra. We don't worry about that. But then what we find, let's see if I. Okay.
So you're going to say that I is an element of this.
That's right. Yeah, because if you look at the geometric algebra G1, G2, no, G3, 0, which is the same thing as the algebra Pauli matrices, then the unit trivector, in fact, is in the center of the algebra. It commutes with all the elements. So it behaves like the square root of -1. So we can say, well, we can say the unit trivector in the geometric algebra G3 is actually in the algebra G3 then, because it's in the center of the algebra. We're making that identification then. So geometric
But here
algebra,
we only have G11, right?
well, that's right. But you see, we're actually generating the geometric algebra G3, because if you look at E1, I times F, that's anti-commutative. E and F are anti-commutative. So E1 and E2 are anti-commutative. And E3, well, all these things, those are just the usual Pauli matrices. We know they're anti-commutative from our experience. But now you see how that arises in terms of the geometric algebra G3, which these are the generators of the geometric E1, E2, and E3. are the generators of the geometric algebra G3. But how,
G-
you see how it's
the
related
basis-
to G11? It's a complexified version of G11, really.
Okay, yes. I was just going to say that you don't have enough basis elements, right? I mean, G11 is only 4-dimensional, but G3 is
That's right.
8-dimensional.
Actually, that's right. So we're complexifying the algebra, and we actually add another,
So
G3
it can't.
has-
So I don't see how. So I can't be an element of G11, right?
well, we can identify it because it's in the center. Let's see if I do that here.
How do
Okay,
you-
so, okay, well, let's go through again. G11 is generated by E and F, and that generates the, well, now it's a subalgebra of G3, but we've identified, look at this, we've identified E2, the vector. Really, that's an imaginary times the F, which has square minus 1. That changes it into square plus 1 then. So you can see we're interpreting any commutativity and all that stuff comes up in a different way, and it means something different each time. This is why I was referring to, you were saying rules are the important thing. Well, actually, that's right. We're really just changing rules, but we're highlighting the
Well-
anti-commutativity.
But complexification, or in this case, is just the same thing as an algebraic extension. Right? You're
That's
just,
right. That's right.
I mean, you just said, give me another element, I, right? And it's
Which has
it's
square
not in
minus
G.
1.
I is
Okay.
not an element of G11,
That's
but
right. That's
but
right.
we know how to multiply it, and when we multiply it, we get G3, right?
And we suppose that's our scalars now. It's complex scalars now, rather than, but of course, geometric algebra G3 is a real geometric algebra because this is the only complex number, I minus I. We're considering the basis over the real numbers generated by E1, E2, and E3 over the real numbers. So even though the matrix has an I in it, it's a real geometric algebra, which, but it's, the real geometric algebra G3 corresponds to the complex 2x2 matrices.
Mhm.
So again, well, okay, that's where confusion can arise too. Okay, and that's what we're doing here. A complex 2x2 matrix G, G11, G12, G21, G2 is in the complex 2x2 matrices. And now you can see I'm doing the same thing with BAA. Well, I'm going to change that to A1 and B1, A1 and B1 to really go over to the geometric algebra G3 then. But again, I'm just using the same rules because I is just, I squared is equal to -1. It's a scalar, commutes, it's in the center of the algebra then. Okay. Well, no.
No, I should.
Well, you can do it. It's off to that. Yeah, it makes noise, but you can try it. Yeah. There might be a little noise. I've got a worker here, but you might bang around a little bit. Okay, let's see. If it gets too bad, I tell them to stop. Okay, so now I want to generalize that a little bit. So again, let's take two Grossman algebras, Gn, which is generated by n anti-commuting vectors, A1 nilpotents, okay? A1 up to AN, they're all nilpotents. They have square 0. And that's why it generates the Grossman algebra Gn, what I'm calling Gn. And then we have a compatible, a second Grossman algebra generated by B1 up to Bn. And we say they're compatible Grossman algebras because they satisfy the rule AI times Bj plus Bi times Aj is equal to delta Ij. Okay, so you can see when Bi, So they're again, with respect to themselves, they're all anti-commutative. The A's are all anti-commutative. B's are but they're also, if the indices are different, like for example, A1, A2, A1, B2, B2, A1 is equal to 0. They're also anti-commutative. So you see, we're characterizing matrix multiplication now in terms of two Guzman algebras compatible nilpotents, A1 up to AN, B1 up to BN, which are compatible because they satisfy this property number 6. Okay, is that clear?
Yes.
Okay. Well, now you see I'm doing the same thing to write the coordinate matrices of this geometric algebra G22, the mother geometric algebras of all other geometric algebras of the same dimension. Okay, so I write 1, A1, A2, A1, 2, and I have two nilpotents, well, two idempotents now, U1 equal to B1, A1, U2 is equal to B2, A2, and okay, and I write them in the middle here, U1, U2, 1, and now notice what I do. I'm writing the same. So these elements are all in the Guzman algebra. But I guess the Guzman algebra usually doesn't have 1 in it, right? A Guzman algebra really, no, I guess 1 is considered to be in the Guzman algebra, right? Is that right or wrong? Does a Guzman algebra GN, I guess it has 1 in it, right? Because a Guzman algebra,
The zero
Okay.
zero form, the zero form or 0.
okay, so right, see,
Degree
these are all
0.
in the basis of the Guzman algebra G2, right? That's the Guzman algebra G2, and then the compatible Guzman algebra B2, well, whatever you, G2 also prime. Okay, call this G2, and this is G2 prime for the compatible one. So this is the basis, the generators of the Guzman algebra is G2, and this is G2 prime because it satisfies the compatible relationship. Okay, so here we have it then. And okay, and now notice what I'm doing here then. I'm doing the same thing. I'm making a column vector out of this. 1, A1, A2, A1, 2 times, this is now, these are commutative idempotents. U1 and U2, they're commutative because, well, again, you know, they're commutative idempotents then. So that's really called a primitive idempotent of G22, the product of these two. Okay, and then I put the Gij in between and this. Okay, okay. So this is the 2x2 matrix. Well, 4x4 matrix, G11 up, you know, G11 up to G14 and going. Okay, I didn't write that out. So Gij is a matrix in the real geometric algebra, M4 over the real numbers then. Okay. Okay, so now we want to, if you want to construct, okay, any geometric algebra can be constructed in the same way by using compatible n by n Guzman algebras. Well, G1, Gn and Gn prime, and putting them together in this way.
Excuse me, I don't, I can't see how do you are using the anti-commutative rule of the first algebra. Because you use the rule that this is nilpotent, but in your first
yeah, okay. So look at these two nilpotents, A and Yeah, they won't anti-commute, but E and F anti-commute, you see? But A1 and A2 anti-commute. Well, again, all the properties of the geometric algebra are reflected in the matrix, the corresponding matrix algebra. Okay, so we have anti-commutative matrices correspond to anti-commutative geometric numbers.
Because your table that you
For example, here, look, E1 and E2 are anti-commutative because the matrices which represent them are also anti-commutative. Okay, so these rules are reflected. If you look at the matrices for A1 and B2, you'll find they're anti-commutative matrices. Okay, all the properties of the geometric algebra are now reflected in the corresponding properties of 4x4 complex matrices or real matrices for G22. Okay, so.
But the starting point was that the algebra represented by A elements is the anti-commutative part of.
Well, but in the first case, I didn't really, A and B are not anti-commutative. A and B are compatible. Okay.
No, but you start your very first expressions.
One more. No. Okay. Here. Okay.
Yeah.
Yeah, the A's are anti-commutative, but in G11 we don't use A. We only use one A and one B. So they're not anti-commutative in G11. Okay. You see, A and B are nilpotents, okay, but they're not anti-commutative. BA is not equal to BA. Well, AB plus BA is equal to 1. Okay, it's only when we get.
But if you have only one element and it's nilpotent, I mean that's trivial, right?
Well, but it's not. It means something.
It's anti-commutative by in a trivial way, right? I mean, A squared is 0. You've already said that.
Oh, okay.
Right.
It's anti-commutative with itself, but
if you have two elements, then being anti-commutative is something different than being.
Well, that's right. It's a generalization of the concept then. Okay, there's still
well, but not a generalization. It's an additional axiom, right?
Okay, that's right.
Right. So if you have two elements, they can both be nilpotent elements, but whether or not they're anti-commutative is
well,
an
that's
additional
right.
assumption.
That's right. That's why I have property number 6. You see, property
but
number
that's
6.
so. But Jesus' question was, did you use this property, right? That they are anti-commutative in the case where you have more than one element, A.
Well,
right?
yeah. Well, I'm assuming that that's why I'm defining them to be algebraically compatible or dual if they satisfy this property. So if the indices are the same, you have A1 times B1 plus B1 times A1 is equal to 1.
Oh, you mean
but A1 times B2 plus B2 times A1, that's equal to 0. Okay, so I am defining.
But you never use the fact that A1 times AJ is right.
Well, that's right. Well, but I assume that I say two sets of linearly independent nilpotents. Okay, so these are linearly independent nilpotents. Okay,
yes.
remember I defined that earlier.
But here those are different from the starting relation that you put. That right?
They're all nilpotents. A1 squared is equal to 0. A2 squared. They're all nilpotents. But they're also
A1 times A2 plus A2 times A1 are not 0.
No, they are
Yes,
zero because of this relate. Oh, yeah. Oh, let's see. I see what you see.
So the question is it an essential assumption, right?
Yeah, that's essential assumption. Yes.
Yes,
Is it?
Let's see if I did I say anything like that? Let's see.
It wasn't clear from your presentation that you used this property.
Well, here you see I say two sets of linearly independent nilpotents.
Okay. Okay.
Okay, where did I define? I guess I didn't define linearly independent nilpotents then, right? Because, oh, right here, look here. A set of mutually anti-commuting nilpotents, A1 to AN, is said to be linearly independent if A1 times up to A2 is not equal to 0. But I say they're mutually anti-commuting nilpotents. So I did say that. I can understand.
But do you need that?
I do need it, yes. Yes, I do.
Because I don't see where you use this property.
Well, I'm using it right now.
Yes.
Right
But
here.
Also to handle the imaginary term, yes.
But you never multiply, in that you never multiply an A with an A.
Yes, well, look, right, yes, I do, right, look, right, this. A1, 2 means A1 times A2. You see?
Oh, yeah, okay.
Yeah, right here. Did I introduce, maybe I didn't, careful. Okay, that means A1 times A2. Okay, and B2, 1 is B1 is right here, look. 1, A1, A2, A1, 2. Okay, I'm
Yeah,
using
where did A12 get defined?
Well, that's in the geometry. This is the Grossman algebra G2. And this is his dual Grossman algebra, the basis of the dual Grossman algebra, G2 prime. Okay, I could have been a little clearer on that. Okay, so I'm writing the first geometric algebra, the first Grossman algebra, that's G2 as a column vector of mutually anti-commuting nilpotents, A1, A2, and A1, 2. Well, you can see that special 1 to 1 is different. And the same thing with B, B1, B2, B2, 1.
I'm trying to find two different Grassmann algebra. One in the first set.
Yeah, I guess that noise is. I can tell him to stop. If that noise is bad, right? Can you hear that noise?
Yes,
It interrupts your speaking.
Okay, I'll tell him to stop.
Okay. Hmm.
Then I'll turn off my mic when the other people speak. Wanda, could you tell him to stop for another 5 minutes and then start again? Yeah, just 5 minutes or 10 minutes. Then the other guy will speak. Okay, I'm sorry. It's.
No.
But I'll be done in another 10 minutes so we can start working then. Well, I want to, of course, hear the next. So you understand now the question that is answered, right? It does follow from my earlier definition here. No worries.
Well, you require that A1, 2
Yes.
be
Remember, I'm
anti-commutative.
characterizing properties of a matrix multiplication in terms of nilpotents or anti-commuting nilpotents. So I do need that. Okay, so that, as you see, two sets of linearly independent nilpotents. Okay, well, that means that, well, again, that's the Grossman algebra is generated, then compatible satisfying this property. Okay, and then I'm defining the more general G22 and the, okay. Well, again, so this is just the geometric numbers then which characterize the geometric algebra G22. Okay, so then the spectral basis I write down in this way. I write 1, A1, A2, A2, 1, 1, B1, B2, B2, 1, and I generate these idempotents, U1, U2. The important thing is that they're products of compatible nilpotents. So everything in a matrix, in the spectral basis of a matrix, is represented entirely in terms of products of nilpotents. That's the main idea. Well, also the idempotents are too. So one can say that, okay, I'm not even talking about a quadratic form here. I am talking about compatible nilpotents and idempotents. So that's the basic structure of a matrix really is defined in terms of idempotents and nilpotents, rather than characterizing by multiplying row and column vectors. But notice how it fits together. The idea of a row and column vector work completely compatible with the notion of geometric algebras. In fact, I define the spectral basis in this way here. Okay, anyway. So, okay, so notice what I call the geometric algebra 2-3. So what we're doing there is we're adding an additional B, okay? So we have, well, yeah, it's a little confusing there. No, I still, okay, no, I'm sorry, what I just said is wrong. So going from the geometric algebra G22, going to the geometric algebra G23, you consider this algebra, you introduce I equal to the square root of -1, okay? Introducing into the geometric algebra G22, you generate the geometric algebra G23, okay? So that's the complexified version with I equal to the square root of -1 as the scalar, okay? So you just complexify this and you have the geometric basis of the spectral basis of the complex geometric algebra. Well, G3 then, well, G2 generated by 2 elements then. G4 rather, I'm sorry. Okay. Okay, so now the Dirac algebra is, I want to characterize the Dirac algebra again by nilpotents and idempotents, or compatible basis of Gaussian algebras then. Well, okay, here I've gone through this before, so I won't spend much time on that. But I'm not completely happy with this basis. I've written that basis down before. But again, what I'd like to do is refer back to this basis. Any complex geometric algebra should be represented in terms of complex numbers in this, changing from G22 to G23. That's the complexified version, but it also applies a Dirac matrix is a complex 2x2 matrix. No, complex 4x4 matrix, okay? The Dirac algebra, the Dirac matrices are complex 4x4 matrices, right? Yeah, mat C over 4, okay? So I should be able to, just by writing this, I haven't quite done that because this is a basis that I've written before, but I'm not completely happy with that basis because we should be able to use 7 just by using complex numbers in here. Well, I try to do that in the next slide. So this is standard material. I've given you this before, so I won't spend time on it. Well, okay, so these are the standard Dirac matrices, you see. So gamma 0 is represented by this matrix. Oh, okay. Notice that might clarify some of the questions that Dr. Cruz had. Notice that the matrix for gamma 0 is just the identity matrix, 2 by 2 matrices here, minus the identity matrix. And then we have the the matrix E1. Well, that's the usual that we had from the previous slide for the Pauli matrices. That's the Pauli matrix here. But now you see J, I'm using J now as the square root of -1 here. Okay. And okay, so these are the standard Dirac matrices then. Sigma K, sigma 0, and that corresponds to the for 1, 2, 3, K equal to 1, 2, 3. Those are the Pauli. This is the 4 by 4 representation of the Pauli matrices then. And this is okay. So that's again with respect to this basis, which I used by identifying U plus minus is this quantity here in the geometric algebras then. So this is again space-time algebra, close to David Hestenes' work. He identifies this as a Dirac spinner, gamma 1, 2. So you'd have to look at, I do give the references for that too. So anyway, so I'm just trying to do that in terms of the A's and the B's, A1 and 1B1. I don't want to spend too much time on this. I will send this. I will say if Dr. Santilli is interested, I'll send him the PDF file. I don't think I sent it to Dr. Santilli. I'll send that to him. So you can see.
It's very interesting, and I find it unique. I think you should correspond with Peter Rowlands because he had importance in his monograph on axiomatic structure of the Dirac equation. I see some connection, but your mathematical treatment is dramatically more advanced mathematically than Dr. Paul Rowland.
Okay, well, okay, I will send that to him. Maybe you could give me his email address again. Short note with it, and I'll send it to him as well then.
It is in the list of participants of this seminar. Peter Rowland, you'll find it there.
Oh, okay, okay, yeah, okay, I'll remember. I'll write that. Yeah, I've met him before, I guess. Peter Rowland.
Peter Rowland, yeah, he will be definitely interested in your work.
Okay, I'll send him that then. Okay, well, these are the standard. I've already given you these references before. Hestenes is, and so on. Okay, so what I'm going to do is I'm going to, any questions, and then I'll let my worker go back to work, and I guess Bill or Jesus would like to talk now some too, would be interesting.
Yeah. I have to apologize with Dr. Cruz, but I see here some commotion in my house. I have some conflict. Very regrettably, I have to leave. But Dr. Cruz, I will appreciate if you can send me, you indicated the availability of a paper. If you can send it to me, I'll definitely look with pleasure. I know that I am interested very much so in the topic of your study on Dr. Otsiewicz. So I have to apologize, but unfortunately I have to go for a house emergency. Okay.
Thank you very much for coming today. And,
of course. I'm honestly very grateful to be very interesting indeed. So thank you to everybody. Again, apologies and thank you.
Okay. Well, I'm not quite sure where to go, but we don't have a lot more time. But Jesus, maybe if you had something in mind, sort of as a follow-up to your presentation from 2 weeks ago.
No, maybe the slides that I sent are related with the presentation of Professor Sobczyk. But and this is why I made some questions, because some of these are related with that. But I am using another approach for this algebra, and after the idea was to connect with the observer algebra. This is the principal
Yes.
subject.
Yeah, so maybe it's useful if you would continue. The sort of comments that I made in the slides that I sent were perhaps on a somewhat different subject. So, but yeah, I would like very much if you could
Okay, maybe
show
I
these
can
slides.
in
You like to share?
yes, I'm going to share, and I am okay. Here is no, excuse me. Okay. The principal idea here is to speak about the observer algebras, but this is too close related with the presentation of Professor Sobczyk. Then this is only some definition of this, but I wanted to stop for a while here. That is the definition of exterior algebra, and I am trying to see some of these properties in the presentation of Professor Sobczyk. Then I am here using some definitions that I find in the book of Young, and about I don't remember the title. I think it's differential forms, but it is related with the Cartan's work. And then here is the two kinds of definition of algebras, and I am trying to find that in the present in the previous presentation, because they define here one algebra and one on the dual of this of this space. And then I am going here, there are two principal properties here that that I was trying to relate, because we have one symmetric property and one antisymmetric property in this vector algebra. These two properties are in the same vector algebra in general, and those are present here, and I think that those are related with the presentation of the interior product and exterior product that are used here. And the other algebra is the algebra of multiforms that are defined in the dual. Then I was trying to find both properties in the presentation before, because for me, both properties are fundamental for the definition of interaction and the definition of observer. Then here we have the.
So can I ask, like when you say you're connecting it with what Dr. Sobczyk presented, are you suggesting just that the exterior algebra can be considered to be Grassmann?
Yes. Yes. Because here we have these kind of properties that are related with the Grassmann algebra. And these are properties of multi-vector forms. No? Those are that we are seeing. Excuse me, here in this slide. And after we have the similar properties here in the multiform space. No? In the space of multiform, we can define one algebra that have this kind of properties that here we have only the anticommutative properties showing here in the bottom part of this slide. And if we take both of these, we can relate them via the Cartan's lemma with the scalar, and is the way that we can go building different levels of the of this algebra. Then I think I was trying to find relations with in this presentation, but I couldn't understand how these both properties in the vector products, exterior products, can. I think that they are related with the two first relations that Professor Garret showed to us, but I don't.
Well, in particular, the Clifford product is often expressed in terms of a symmetric part and an anti-symmetric part.
Yes, like I think that here we have both parts of this product, the symmetric and anti-symmetric part, and we are in this moment in the exterior product of vectors only. We don't need here the dual for this definition.
This notion of dual also is interesting, right? Because we think of forms as being dual to vectors in the sense of dual space, dual linear space. But this notion of duality is different than what Dr. Sobczyk.
I don't think there's much difference. I think that the standard definition is just you have a space, a vector space, and you have its dual space. But here, that the relationship AB plus BA is equal to 1. That's where the difference is. And that's what makes possible a quadratic form of a Clifford algebra. Whereas you're just a dual space is, is just a different algebraic quantity that you're stressing this division, which I'm not, in Clifford algebra, you don't do that because you put a vector with square minus 1 on the same footing as a vector with square plus 1. They can be anti-commuting, or so it's much more restrictive. I think the standard definition of duality is a separate vector space which maps vectors onto scalars, and that's it.
But that requires a category in which you have evaluation, so you can evaluate the vector by a form, right? You have some operation between vectors and forms that actually generates the dual, right?
Yeah.
But you're defining the dual in a without ever having to talk about evaluation.
Yeah, I'm saying they're compatible Grossman algebras. The definition of that one definition there is expression of duality, really.
But I understand that if we go to different degree here in the product, in the exterior product, when you go building the different degrees in the product of vectors, then you are going to different Grassmann algebras. I think it's the same, no? It's the same.
Mm-hmm.
But then we have here two kinds of algebras, the algebras of vectors and the algebra of covectors.
Mm-hmm.
And then with these two, we have the evaluation of this that are related, these two algebras in the scalar fields, through the scalar fields. And
Yeah. Mm-hmm. Yeah, that's, for the first Q of them, it's kind of like the compatibility, I believe, right? You're not, with P not equal to Q, at that last relationship, if P is not equal to Q, then it's equal to 0. So that's like the compatibility statement, I think.
Yes, I think we can relate to that, but we need here the scalar forms, because without the scalar forms we can go, we can get this. And this is important here because this is used after for building the algebra of the Grassmann algebra via derivation of this algebra. Because if we use that, then we can use this kind of evaluation in the operation between vectors and covectors that are related with this building of algebra. This is made here for the creation operator, for example. We can introduce this operator, and the annihilation operators that are the way that we can go to different Grassmann algebra. Those are very important for the building of the observer field. Because the observer field is built with these two parts of the split of the space. One part in covector and one part in vector form, or better, one part in the kernel and one part in the image of the space. Then this is the idea that I was using in the definition of observer when I try to define using the idea of the interaction. Then we can use that here, and this was used after for the for build the structure of the one observer that is fundamental for the for work the physical laws in terms of one observers and for relativity in general too. Then this is the principal ideas that I wanted to present to you, trying to relate with the presentation of Professor Sobczyk, because I think that we can find many things that are related in this formulation, but that I don't get to all of them in this time. Then
one difficulty I have always at this point is the introducing the notion of time life at this point, right? Because we have no mention of a metric here yet, right? So I am not sure what we can mean when we say time-like here.
But this is the idea that excuse me, I need the pen for right here, excuse me. Because we don't need the metric tensor for the definition of time, because here the idea is that the space can be split in two parts. I think that this is the important thing. The important thing is that if we describe not like one observer, but like an event, then this can be expressed by one tensor product that is generating all the space. Then in this previous slide here, we have here the definition. we are only splitting here the space. And then we did not hear the the metric.
So this distinguishes kappa here, right? Yeah,
Yes.
as something special, right?
Because we can split the space either if I have one n space, then we can split with the product of one form of n minus one degree with the one vector of degree 1. And I think this is doing here for observer. Is one splitting of the space in this way with these properties, of course. I remember that Professor Osiewicz likes to write this in this way. Here, I have F, and here I have the Grassmann algebra via E, and then I get here one form of degree 1. And so then we can get here to don't remember, but I am using this in general. Excuse me.
This E operator is the creation operator, right?
The creation operator. I think that it is better to use that.
In each case, it's just reducing the dimension of the original space by 1 by you're taking out.
Yes,
increasing.
So
in this case, it's increasing.
Okay, yeah, so it looks like it could be represented as a general type geometric product. And Clifford, I don't think I think it would be possible to reformulate this in the way I look at things too.
Yes,
but you also have the dual, right?
But here we have the dual, and here I have the dual. Here is the creation operator, and we can find one creation operator that is the dual of before. And here we have 2 and so. And the metric is relating here. D and G minus 1. but we can work here and here without looking about the relation of via the metric.
So this 1-1 tensor kappa or endomorphism incorporates well, how do we add it to this drawing, right? We can't easily add it, right? Because we need to make a tensor.
Because if we are, for example, here, this kappa can split this because maybe I can go to the next slide here, because this was expressed here. If I have one differential form, I can split this differential form into two parts here. Then any differential forms can be written in this way. And of any dir grade. And then if we express a physical law in terms of a differential form, then we can split in this way. Then the decomposition is in space-time is only algebraic without using a metric.
Yes.
Here.
But this, well, yes, I like this, but the reason why I asked the question, I guess, is that it always causes me some conceptual discomfort. Like I'm not comfortable always to say that this splitting is how we define whether something is time-like or not.
The splitting is the way that we define observer. That is idempotent. This is the way that we can split this form. And the observer is wielded with the splitting of the space, of the entire space.
Yes, I think it's good. I agree with this approach, but I like better the idea that Ushevich introduced of the algebra map and the algebra derivation, so that the time-like part comes from the derivation part of the split. Maybe it's just a little bit of an elaboration, but
The interesting thing is with the Hessian's approach is the splitting of the Dirac algebra into the even subalgebra, which is the polyalgebra of an observer. So I'm sure these ideas map together, but it's just a different way of looking at it.
But you see, it's important here to notice that there is no quadratic form, no metric involved in this definition.
Okay, but remember the definition I gave, I used idempotence and nilpotence, but there was no real metric there either. You're just saying that there's the matrices are just products of idempotence and nilpotence, no metric. But if you want to, I don't think that the quadratic form is really such an important idea, really. But anyway, that seems to be the crux, though, of the problem. One where you're worrying, oh, it's a quadratic form, but no, really, a matrix, as we just saw, is just a product of nilpotence and idempotence. You don't have to say there's a metric involved.
So, is there some expression in the Clifford algebra or the geometric algebra that corresponds to an endomorphism?
Sure, just a linear mapping. So, maybe I could say something about that. There's how that, I can say something about that. There's actually two ways of looking at that. And not very difficult, really. I could spend 15 minutes on that next time or something.
Jesus, could you return to the previous slide, I think?
Here?
Yes. Yes. Okay. And so what I would be interested to see is this the formula that's highlighted here, that alpha is split in this way. So how do we do something like this in geometric algebra? So we need to be able to define
each algebra splits the Dirac algebra in a different way. Identifies what's a vector and a bivector for one observer is different from another observer's point of view, and that all follows from, like I say, each observer splits the Dirac algebra into the polyalgebra in a different way as an even subalgebra. The elements are the same, but they're reinterpreted in terms of bivectors and vectors in a different way. So it must be equivalent. There can't be any difference, really.
Yes, I think it's very interesting to see the Clifford algebra or geometric algebra, or maybe I should give you a little bit of a challenge that if you present Clifford algebra in this form, is it still reasonable to call it geometric? I mean, since as you've just admitted, there's no need to define a quadratic form or to define what you mean by metric. You're doing something that's sort of intrinsically algebraic.
Well, no, I'm not going to say not to use quadratic forms, but it's just another way of looking at things. Each observer defines his quadratic form, which is different from the other observers. So I think it makes a lot of sense. As I say, if you look at an electric field or electron, it's just a charge, you just see an electric field. But if you move that charge, then you've got a bivector involved. And you can see in time you're sweeping out a vector becomes a bivector. That's exactly what a bivector is. But that's observer dependent idea.
But I think I do see potential sort of problem is that the second term here is space-like in the sense that it constitutes another in this case Grassmann algebra, but the first term is not, right? The first term is something different. It's
No, I just think that a quadratic, the idea of a quadratic form is not such a rigid idea. I mean, for example, okay, you start with the Dirac algebra. Okay, well, that's the Clifford, that's the identified with 1, 3, the metric as a quadratic space, a quadratic form. But that's picking out a timeline. Each time-like vector gamma 0 defines a rest frame. Well, you know, it's just slightly different way of looking at, but I think it makes sense. As I say, electric field is one thing, but if an observer is moving, then it mixes together with a bivector. Well, that's like mixing a quadratic form, really, as far as the observer is concerned. So it's not such an important idea there, I don't think. But anyway.
well, alpha is like an n-1 form, right? Alpha S is
Not necessarily. Here there are another question because the idea is that in general we have two kinds of laws of physics. One is related with the interaction field, and the other is related with the properties of matter. And then these two laws are with of degree of complementary degree. They are of complementary degree. Because from these two laws, we can describe the system in the space, in the space-time. This is the idea. Then when I speak about the interactions, we use it two kinds of laws. One related with the one form, and the other related with a vector form. And then the product of both are related with, for example, the energy of the system. Then not necessarily the alpha have a degree n-1, no, not necessary.
well, I like to see in alpha S, alpha sub S, another Grassmann algebra. Right? It's the Grassmann algebra of space, right? Whereas
Yes.
kappa is the comes from the or I should say alpha comes from the Grassmann algebra of space-time. So that
Alpha
okay.
T, what does alpha T come from?
well, that's the question. That's what I like.
Properties of the system.
Yeah, it here it comes as this difference, right? As this alpha minus kappa alpha, right?
Yeah, but here the idea is that alpha have this property. D alpha is equal to 0, or the alpha is equal to to G. And then dg is equal to C. Mhm.
I'm not sure I understand.
What is G?
G is a potential, a potential related with alpha.
But you write
Because-
D is exterior product, exterior derivative.
Yes, D is exterior derivative. D have the properties this. Mhm.
Yes. And so G is
Yeah, in Clifford algebra, you use the gradient operator, and you can have the divergence and the curl are put together. That's the same thing like the geometric.
yes, it's the same. It's the same
So
concept
again,
here.
you can represent all these things in differential geometry, but again, you're always separating vectors, covectors as a different language is what it comes down to.
But the exterior derivative of alpha is the degree n+1.
The exterior product of, excuse me,
Exterior derivative is degree n+1.
Okay,
Yes.
and how do you decrease what's the dot product? It knocks down the degree by 1. That's the creation and annihilation operators, I guess, right?
Annihilation, yes.
yes.
Yeah, different way of looking at things is what it comes down to. Different
Right.
languages. That's the whole problem. Just like there's so many different languages in the world, that's the problem.
Well, a lot of this language, of course, that Jesus is presenting here is the same as what I had in the slides that I sent out this morning. Of course, it comes from Olszewicz originally,
Yes. Mhm.
or the work between Jesus and Olszewicz, and in particular, the subject of the observer algebra is embedded in one of the papers that you published with Olszewicz, I think, Jesus.
Yes, it is in I don't remember, maybe there are 2 or 3 papers that we published with this subject. One of them was the related with the Maxwell equation for any kind of non-holonomic observers. Mhm.
Yes.
Um,
I viewed Olszewicz's last papers, I think from about 2017, as a kind of generalization of that work. He was looking, I think, at sort of the central algebraic part of it, in sort of so with this definition of the creation and annihilation operators, he was able to construct these maps, the algebra map and the algebra derivation. That was the subject of the first part of the paper that I referenced in my slides. And that, to me, I found that kind of generalization, well, it's not really a generalization, but it's kind of a distillation of the essential part of the Grassmann algebra that is necessary in order to construct this kind of splitting operation. And so if you can abstract these types of mapping so that we're mapping from one algebra into another algebra, and then we look at, like, given that mapping, we can look backwards along that mapping to see what that implies, right? So
It goes back to the question of that we were trying to get at, of why what 3 observers are necessary that we talked about, where, in your talk and in the conference.
Yeah, it's, well, I'm not sure it's so directly connected to that, but it's connected to the idea that this notion of binary velocity, of relative velocity being a binary concept, is sort of a intrinsic definition. It's something that comes directly from the algebra alone, right? Whereas the notion of ternary velocity is something more complicated, and it's what distinguishes conventional relativity from the form of relativity that Oshevich was developing.
So are they equivalent or not equivalent?
Not equivalent.
Not equal. So can it be tested then? What it would be a test? Or maybe Zbyszek had a test. I don't remember.
Yes, there were some published proposals for the transformation of certain electromagnetic fields. But the experimental tests were difficult, to say the least. Like there was only high order differences in the expressions. So, but I never looked too deeply at that. I was more interested in the conceptual sort of foundations.
Yeah, it would be interesting if we could see how to formulate it with this compatible Grossman algebras as I look at that upon.
Well, yeah, I think that's potentially very interesting. But in order, I'm not sure of a. What I would like to see maybe is how to understand mappings between Clifford algebras, between geometric algebras, so we would like to have, say, G11 as so we'd like to say something like G11 plus something is G3, right? Or we would like to say that between out of the Dirac, like you said, out of G13, we can split out G3, right? But we want to do that in a way. So if we split out G3 from G13, what's left over, right? So it's the same expression here. Like, so if we split out the alpha sub s as being the same thing as G3, like in the algebra of G3, then what algebra is alpha t? Like alpha t is an element of what? Is it? I don't think it's an element of another Clifford algebra, but I might be wrong.
Right now, the way it goes is the element of another Grossman algebra, if I'm not mistaken, and how things look right now with Dr. Cruz's presentation. It's another Grossman. We're only talking about Grossman algebras. Well, I know, I guess covectors are well, no, that we make the Grossman, a covector is part of a Grossman algebra. That's the compatible Grossman algebra to a given Grossman algebra, as I see it.
I was trying to think about this, and I think that we can understand this splitting that was made here, like a vector-covector splitting. No? I think that we are doing that, and then we can take the vector part and this have his algebra, and the covector part has another algebra. But I understand the question of Professor Page, and then we need to demonstrate in this splitting of this differential form that one part is follows one vector algebra, and the other part follows a covector algebra. I think that it is needed.
Yeah, I think that's correct. So Doctor, I've had these conversations with Dr. Ojevich too for many years. It's just differential forms, okay, covectors and a vector space and its co-space. So yeah, it's a much more rigid with the geometric algebra. That's why it's not such a rigid structure, but the same things are there. You can interpret it in a different way. You can interpret it as a quadratic form or whatever, but the same structure is the same structure as a linear space or a matrix.
I mean, another way of stating it perhaps is that I can see how the image of an endomorphism can be like this, how should we call it, the space-like part of the, so this under the image we have something times another algebra, right? But under the kernel, we don't have this something times another algebra. We have this odd looking thing that is the difference. And that doesn't factor nicely, right? It's so it's something that doesn't, so the kernel as a space has different properties than the image as a space.
Well, the kernel really consists of the covectors, if I'm thinking about it right.
I'm not sure. Anyway, I think maybe now is a good time to stop our meeting for today. And they've two talks so far sort of fit together quite well, and maybe some of the things that I can present, say in our next meeting, could at least follow along from this from Jesus's presentation. But I still look forward to understanding this in using the methodologies that you presented, Dr. Sobczyk.
Yeah, I might be able to say a few things about endomorphism that you were asking questions about, and say how anything that really from standard linear algebra translates immediately. Once you can translate a matrix into a geometric number, anything, I can show you how to translate anything from matrix algebra to a corresponding expression in geometric algebra. So I'll show you maybe a couple of things there I can prepare.
Yeah, so these notions are well defined in matrix algebra, at least from usually not in so abstract a form as this, but so in matrix algebra we need to be able to think about operators between linear spaces, right? And they're
Exactly.
the kernels of these operators.
Exactly.
Okay, well, right now for me, our schedule of meeting every 2 weeks is quite good, I think. I'm fairly busy with other things this time of year, and so
Yeah, I think that's good. Yeah, I'm the same way, really. I've got a lot
Okay.
of things I've got to do here.
okay, so we could agree then that in 2 weeks' time, I can give some presentation, say to start with, and then maybe we can have some discussion and comments connected to our presentation today.
Sounds
Okay.
good to me.
All right.
Okay.
So thank you very much, and I hope everyone stays well and has a interesting summer. Yeah, well and happy. That's correct. Yes.
Okay.
Okay.
Thank you.
See you in 2 weeks' time.
Okay.
Goodbye.
See you.
I see you.
Bye bye.
Bye.